Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is source conversion. Our objective today is to introduce a circuit analysis technique known as source conversion, where a voltage source in series with a resistor is exchanged for a current source in parallel with a resistor, and vice versa. This lecture is meant to be a follow-up application to the current sources lecture available at the Big Bad Tech channel. If you haven't watched this lecture yet, or perhaps only dimly recall its contents, I'm asking you to do so now. Additionally, this lecture is predicated upon the belief you are skilled in the use of both the VDR and CDR techniques. These lectures are also available at the Big Bad Tech channel for your review if required. Source conversion is a very easy circuit analysis technique that allows one to exchange a current source in parallel with a resistance for a voltage source in series with a resistance without otherwise affecting circuit behavior. This technique is also bidirectional, in that a voltage source in series with a resistance can also be exchanged for a current source in parallel with a resistance without otherwise affecting circuit behavior. Source conversion allows a degree of flexibility in circuit analysis scenarios and allows one to employ certain circuit analysis techniques in preference to others. Sometimes you want to use the VDR. Sometimes you want to use the CDR. Source conversion allows you this choice. The principal technique for changing a voltage source in series with a resistor to a current source in parallel with a resistor is establishing an equivalency for the two terminals these different source configurations use to interface with a load resistor. Ideally, anything attached to these two nodes should be unaware that the source conversion has occurred and will continue to operate as previously. To change a current source in parallel with a resistor to a voltage source in series with a resistor, we need to solve for the magnitude of the voltage source and resistor value that would maintain the equivalency when this new source is attached to the same two nodes. First, we need to remove the load resistor and isolate the current source and the parallel resistor. The value of the series resistor, you'll be happy to know, is the value of the parallel resistor. Only the position changes. If this is a 400 milliampere current source and this is a 60 ohm resistor, the resistor in series with our as of yet undetermined voltage source is 60 ohms. Tracking so far? To determine the value of the voltage source, solve for the voltage across the resistor in parallel with the current source when isolated from the load. When isolated from the load, there is no other current path, and the current source would push all 400 milliamperes through the 60 ohm resistor and via Ohm's law induce a 24 volt drop across it. Our voltage source is therefore 24 volts. Now we can reattach the load resistor. If everything I've said is true, this 24 volt source in series with a 60 ohm resistor will induce the same voltage drop and current through the load resistor as would a 400 milliampere current source in parallel with a 60 ohm resistor. Let's assume our load resistor for both scenarios is a 100 ohm resistor. From the perspective of the original 400 milliampere current source in parallel with a 60 ohm resistor, this is clearly a scenario befitting application of the CDR. This CDR is set up to solve for the current through the 100 ohm load resistor is as follows. We find that 150 milliamperes of current travels through the 100 ohm load resistor when placed in parallel with a 60 ohm resistor and a 400 milliampere current source. We can use Ohm's law to solve for the voltage drop across the load resistor. Substituting in the necessary values, we find the current source configuration induces a 15 volt drop. From the perspective of the converted 24 volt voltage source in series with a 60 ohm resistor, this is clearly a scenario befitting application of the VDR. The VDR is set up to solve for the voltage drop across the load resistors as follows. Substituting in the necessary values, we also find a 15 volt drop across the 100 ohm load resistor. We can use Ohm's law to solve for the current through it. Substituting the necessary values, we find this source configuration induces 150 milliamperes of current as anticipated. Equivalency has been maintained and the 100 ohm load resistor is none the wiser that the original current source in parallel with a 60 ohm resistor has been swapped out for a 24 volt source in series with a 60 ohm resistor. Notice the voltage source's positive terminal is pointing up, as was the current source's directional arrow. This ensures even the polarity experienced by the load resistor for different source configurations is the same. What about the opposite scenario? Let's say we've got a voltage source in series with a resistor, and we want to swap this out for a current source in parallel with a resistor that will produce equivalent output to our load resistance. We need to solve for the magnitude of the current source and resistor value that would maintain the equivalency when this new source is attached to the same two nodes. First, remove the load resistor and isolate the voltage source and the series resistor. The value of the parallel resistor, you'll be happy to know, is also the value of the series resistor, only the position changes. If this was a 120 volt voltage source and this was a 1 kilo ohm resistor, the resistor in parallel with our as of yet undetermined current source is also 1 kilo ohm. Tracking so far? To determine the value of the current source, solve for the magnitude of current induced by the voltage source when the two terminals are short-circuited, i.e. when there is nothing limiting current besides the series resistance. Substituting in our given values, we find our current source to be a magnitude of 120 milliamperes. Now let's reattach a load resistor and see if everything I've said is true. If so, a 120 milliampere current source in parallel with a 1 kilo ohm resistor will induce the same voltage drop across and current through the load resistor as would a 120 volt voltage source in series with a 1 kilo ohm resistor. Let's assume our load resistor is a 2.2 kilo ohm resistor. From the perspective of the original 120 volt voltage source in series with a 1 kilo ohm resistor, this is clearly a scenario befitting application of the VDR. The VDR is set up to solve for the voltage drop across the 2.2 kilo ohm load resistor is as follows. Substituting in the necessary values, we find an 82.5 voltage drop across the 2.2 kilo ohm load resistor. We can use Ohm's law to solve for the current through it. Substituting in the necessary values, we find the current flowing through our load resistor is 37.5 milliamperes. From the perspective of the converted 120 milliampere current source in parallel with a 1 kilo ohm resistor, this is clearly a scenario befitting application of the CDR. The CDR set up to solve for the current through the 2.2 kilo ohm load resistor is as follows. Substituting in the necessary values, we find that 37.5 milliamperes of current travels through the 2.2 kilo ohm load resistor. We can use Ohm's law to solve for the voltage drop across it. Substituting in the necessary values, we again find a voltage drop across our load of 82.5 volts. Equivalency has been maintained, and the 2.2 kilo ohm load resistor is none the wiser that the original 120 volt voltage source in series with a 1 kilo ohm resistor has been swapped out for a 120 milliampere current source in parallel with a 1 kilo ohm resistor. Again, notice the current source's directional arrow is pointing up, as was the voltage source's positive terminal. This ensures even the polarity experienced by the load resistor for the two different source configurations is the same. There's really not a whole lot more I can say about source conversion other than this. Pause the lecture and take a shot at converting these sources to their other world equivalent. If it's a voltage source in series with a resistance, change it to an equivalent current source in parallel with a resistance. If it's a current source in parallel with a resistance, change it to an equivalent voltage source in series with a resistance. Ensure equivalency is maintained by solving for the voltage across the load and the current through the load for both configurations. Ideally, either configuration will induce the same voltage drop and current through the given load resistance. Make sure polarity is accounted for such that either source configuration induces current through the load resistor in the same direction. I won't go into great details about the techniques I use to arrive at these answers, since the steps used are identical to our previous illustrated example problems. If you've done everything correctly, a 27.6 volt voltage source in series with a 1.2 kilo ohm resistor is equivalent to a 23 milliampere current source in parallel with a 1.2 kilo ohm resistor. Either configuration should induce approximately an 18.6 volt drop across the given 2.5 kilo ohm load resistor and approximately 7.5 milliamperes of current through it rounded to the 10th place. Notice the polarity of the current source is oriented such that the directional arrow is pointed downwards in accordance to the positive terminal of the original 27.6 volt voltage source. Voltage, current, power, and even polarity delivered to the 2.5 kilo ohm load resistor is exactly the same, and the load resistor is oblivious to the fact a different source configuration is being used. Finally, if you've done everything correctly, 50 mA current source in parallel with a 700 ohm resistor is equivalent to a 35 volt voltage source in series with a 700 ohm resistor. Either configuration should induce approximately a 12.7 volt voltage drop across the 400 ohm load resistor and approximately 31.8 milliamperes of current through it rounded to the 10th place. Note the polarity of the voltage source is oriented such that its positive terminal matches that of the directional arrow of the original current source. Voltage, current, power, and even polarity delivered to the 400 ohm load resistor is exactly the same, and the load resistor is oblivious to the fact a different source configuration is being used. We'll make use of source conversion in later circuit analysis scenarios. It's a simple and effective means of making circuits easier to visualize and analyze. Notice we applied either the CDR or the VDR when we made the conversion. If you overwhelmingly prefer one technique to the other, you have my permission to do a source conversion and make it happen. Either configuration should yield identical results. In conclusion, this lecture presented the circuit analysis technique known as source conversion. Source conversion allows a degree of flexibility in circuit analysis scenarios and allows one to employ certain circuit analysis techniques in preference to others. Remember to review this material as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.